The James Webb Space Telescope, commonly referred to as JWST, represents one of humanity's greatest achievements in space exploration and technology. Launched in December 2021 after decades of planning, engineering, and anticipation, it is the most advanced infrared-focused observatory ever placed into space. The telescope is the product of a global giant collaboration with all the expertise and resources of NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. Its design and capabilities render it singular, not just the largest space telescope ever built but also the most powerful. By looking mostly at infrared light, JWST can see further out into the universe than any other previous observatory, observing images and data that offer a glimpse into the first galaxies, the formation of stars, and planetary systems. Scientists had dreamed for a long time of having such an instrument to replace the Hubble Space Telescope, and JWST does just that, pushing astronomical exploration to a whole new level. Part of what makes JWST so exciting is its ability to see wavelengths of light that the human eye can't detect. Whereas Hubble, which was launched in 1990, revolutionized our knowledge of the universe with its stunning photos in visible and ultraviolet light, JWST extends that by concentrating on the infrared spectrum. Infrared radiation is especially helpful in astronomy as it can pierce through cosmic clouds of dust that tend to block visible light, detecting stars in the formation process and planetary systems in the making. It also enables astronomers to observe the vastly distant galaxies whose light is stretched into the infrared by the universe's expansion. In a way, JWST can almost be considered a time machine that allows us to observe the universe as it was billions of years ago, mere hundreds of millions of years after the Big Bang. While JWST was not specifically designed to observe planets in our own solar system, it has nonetheless given us some of the best and most resolution-enhanced images of those bodies ever accomplished. A particularly interesting example of this is its observation of Pluto. Pluto has long been a popular figure in people's imaginations, previously regarded as the ninth planet of the solar system before being reclassified as a dwarf planet. The fact that JWST is capable of observing Pluto in infrared light has given astronomers fresh and detailed information about its surface and atmosphere. By looking through the thin, but foggy, veil that envelopes the cold planet, JWST has uncovered information regarding Pluto's surface chemistry and specialized geology, providing a precision never previously achieved by telescopes on Earth. Pluto itself has a fascinating and rather melodramatic history in astronomy. It was originally found on February 18, 1930, by American astronomer Clyde Tombaugh at the Lowell Observatory in Arizona. The find was the culmination of a quest started by Percival Lowell, who had speculated the existence of a mysterious planet X that he guessed was affecting the orbits of Uranus and Neptune. While Pluto proved to be much smaller than Lowell had anticipated for Planet X, Tombaugh's find was still proclaimed as monumental. Scientific bodies worldwide soon declared Pluto to be the ninth planet of the solar system, and Pluto was officially named after a suggestion by a British schoolgirl, Venetia Burney, who was 11 at the time. Pluto was hailed as the farthest planet, wandering around the edge of the solar system in an area that later became known as the Kuiper Belt, for decades. But Pluto's status as a planet came into question as more and more discoveries were being made in the outer solar system. Starting in the 1990s, astronomers discovered other small, icy objects in the Kuiper Belt, some comparable in size to Pluto. The discovery of Eris in 2005, an object slightly larger than Pluto, compelled astronomers to re-examine the definition of a planet. The International Astronomical Union, IAU, in 2006 made the controversial move of demoting Pluto to a dwarf planet. The IAU specifies that for a body to qualify as a planet, it must meet three requirements: it must be orbiting the Sun, it must be roughly spherical in shape as a result of its own gravity, a state referred to as hydrostatic equilibrium, and it must have removed other debris from its orbital zone. Although Pluto satisfies the first two requirements with ease, it does not orbit in dominance, as others of the Kuiper Belt objects share its orbit. Therefore, it was reclassified to dwarf planet status, which continues to be a point of controversy and passion for many people who grew up studying Pluto as the ninth planet. Still, this reclassification has not dampened Pluto's appeal. In 2015, NASA's New Horizons spacecraft performed a historic flyby of Pluto, becoming the first mission to visit the distant world. The images and data returned by New Horizons completely transformed our understanding of Pluto. Far from being a barren, frozen rock, Pluto revealed itself as a complex and dynamic world with an astonishing variety of landscapes. The spacecraft's photos revealed expansive nitrogen ice plains, rocky water ice mountain ranges, and a dramatic heart-shaped feature now called Tombaugh Regio after its discoverer. This frozen heart, about as big as Texas and Oklahoma combined, is primarily made up of nitrogen and methane ices and is one of the most recognizable features of Pluto. The New Horizons mission also showed Pluto's surface to be geologically active, with signs of glaciers, tectonic activity, and even the possibility of cryovolcanoes. The results indicated that Pluto is not a dead planet by any means. It is actually one of the most geologically rich bodies in the solar system. What adds to the interest of Pluto is the potential for a subsurface ocean of liquid water under its icy exterior, shielded from freezing solid by internal heat and insulating ice layers. If it is the case, it will make Pluto another contender in the quest for extraterrestrial life, adding moons such as Europa and Enceladus to the increasing number of icy bodies potentially possessing hidden oceans. Pluto's surface also displays signs of previous climate change and geologic activity, with land that seems to have been remodeled over time. One of the especially intriguing findings is that Pluto possibly experienced an actual polar wander, which means its whole outer crust moved relative to its rotation axis. Such a radical shift could account for some of the strange alignments of its surface features, particularly around the western lobe of its heart-shaped glacier, Sputnik Planitia. One of the most notable surface features are narrow, blade-like ridges made of methane ice. These rugged landscapes are considered to be the result of sublimation, a process by which ice is converted directly into gas as a result of climate fluctuation on Pluto. Their presence points out the sensitivity of Pluto's surface to changes in its tenuous atmosphere and the dynamic activity that carves it. These findings prove that even a diminutive, far-off dwarf world can have astounding geological complexity, matching the giant planet moons for diversity and scientific value. As New Horizons continues to return data, scientists are finding more secrets, not only about Pluto but also about the numerous other icy bodies that populate the Kuiper Belt and beyond. While New Horizons gave an up-close look at Pluto, telescopes such as JWST supplement this effort by still monitoring Pluto at a distance. Using its infrared eyes, JWST provides a whole new window into the world, offering information on Pluto's surface composition, atmospheric structure, and seasonality. These observations are precious because they enable researchers to monitor Pluto's evolution over time, long after New Horizons has flown by. In addition, JWST is also examining other outer solar system worlds, assisting astronomers in reconstructing a more comprehensive understanding of the solar system's outer reaches. Another of the most thrilling recent accomplishments of JWST has been observing Neptune, the solar system's eighth and farthest known planet. Neptune has long fascinated scientists due to its enigmatic atmosphere, intense winds, and weak ring system. Neptune was discovered in 1846 as the first planet to be discovered by mathematical prediction as opposed to observation. Astronomers detected anomalies in the orbit of Uranus that indicated that there must be an unseen planet, and calculations pointed them toward Neptune's position. By the time it was observed with telescopes, the prediction had been fulfilled, and this was one of the great advances of 19th-century science. It is commonly represented as a deep blue planet, thanks to the pictures taken by the Hubble Space Telescope and the Voyager 2 spacecraft, which passed by Neptune in 1989. It is the methane in its atmosphere, which scatters red light and reflects blue wavelengths, giving it that deep blue appearance. But JWST's infrared view has shown Neptune in a new perspective. Rather than the bright blue commonly attributed to the planet, images from JWST reveal Neptune as a fainter, ghostlier world. These observations have revealed bright, mottled features in its atmosphere, methane ice clouds that exist at high elevations where it gets cold enough that methane condenses. These clouds shine particularly brightly in the infrared because they reflect so well. With these observations, scientists are being provided with important insights into Neptune's atmospheric processes, such as cloud motions, weather patterns, and seasonal variations that have thus far been elusive. Even more astounding is JWST's imagery of Neptune's rings. While Neptune's rings were first suggested in the 1960s and later unequivocally established by Voyager 2, they have consistently been challenging to research because of their faintness. JWST's infrared high-resolution images have given us the best look at Neptune's rings in decades, revealing them with greater clarity and detail than ever before. The observations not only verify the previous findings but also provide greater insight into Neptune's ring system as well as the encompassing dust bands around the planet. Through observing these structures, astronomers expect to gain more knowledge about the mechanisms that create planetary rings and how stable they are in the long term. The observation of Neptune and Pluto by means such as JWST illustrates how much remains to be discovered about the outer solar system. These far-off worlds, once conceived of as stationary and boring, have turned out to be dynamic, intriguing, and profoundly captivating. Combined, the discoveries of space-based telescopes and flyby missions such as New Horizons are revealing a solar system much more varied than previously envisioned. From the frozen core of Pluto and changing landscapes to Neptune's ethereal rings and stormy weather, the outer edges of our planetary community keep surprising and captivating. In the larger context of astronomy, these findings also serve to remind us of the need to continue to extend the horizons of discovery. JWST not only is unlocking the secrets of the universe's first galaxies but is bringing new insights to the planets and dwarf planets within reach. Each observation leads to a greater understanding of the universe and humanity's place in it. The exploration of Pluto and Neptune, as much as it is an individual mission to individual worlds, is also a prelude to larger questions. How do planetary systems develop and age? What conditions make for a geologically active planet? And could there be environments within our solar system, or elsewhere, capable of supporting life?